Welcome back. Today we are covering indeterminate forms and L'Hopital's rule. You had learned in Calc 1 how to handle the limits of different functions, and we're going to continue that and expand that. You had the indeterminate forms, which you didn't know what to do. You had started off with some different ideas, and then you'd factor to see what you can and can't do. So we're going to look at this and we're going to start saying, well, I want to find the limit as x approaches infinity of 2x squared plus 5x minus 1 divided by 7x squared minus 3x plus 2. As you can see in here, it says about the major players. The major players are the terms with the highest exponent. So in this case, it'd be 2x squared and 7x. In Calc 1, you had learned you would divide everything through by, in this case, 1 over x squared and 1, or multiply everything by 1 over x squared and 1 over x squared, because you were looking at the largest uh, exponent variable in the denominator. Well, in major players, we can avoid that whole idea because you'd still end up with the same thing. You'd end up looking at the limit as x approaches infinity of 2x squared over 7x squared. That reduces to 2/7, and we're claiming that the limit for this function is 2 over 7. Doing the same thing using the major players, we're going to look at the limit as x approaches infinity of just 3x squared over 4x cubed. Reducing that, I get 3 over 4x. Well, as x approaches infinity, the denominator gets larger and larger and larger, and the whole thing approaches 0. Here's another example, looking at the limit as x approaches infinity of 4x cubed over 2x squared. Reducing that, I get a 2x over 1. As x gets larger and larger, the whole thing, the numerator gets larger and larger, so the whole fraction approaches infinity. So the limit for that would be infinity. Now, major players is great, but it only works as x approaches infinity. If x is approaching a specific value, you can't use major players. And so what happens is sometimes I'm approaching infinity, or maybe I'm just approaching a specific value, and I'm still in indeterminate form. This is where L'Hopital's rule comes in. It says suppose f and g are differentiable, and that the derivative g of x is not equal to 0 near a, except possibly at a itself. So it says suppose the limit as f of x, the limit as x approaches the infinity of f of x equals 0, and the limit as x approaches the infinity of g of x equals 0. Well, if I had a fraction, that would give me a 0 over 0. Or it says, what happens if the limit as x approaches infinity of f of x is equal to the positive or the negative infinity, and the limit of g of x, limit as x approaches infinity of g of x of positive infinity? Again, I'd end up with a positive infinity over positive infinity. And that was an indeterminate form that we didn't know how to deal with before. We would factor or do what we could. And again, it says, in other words, we have an indeterminate form of that sort. We're going to look at this and say the limit as x approaches infinity of f of x and g of x, if it approaches 0 over 0 or infinity over infinity, I could then just take the derivative of f of x and the derivative of the g of x. I am not using the quotient rule. I am going to take just the limit of the f of x, and then I will take the limit of the g of x separately. It says if the limit on the right side exists, or is infinity over, so then they're the same limit. So the idea again is I'm just going to take the derivative of what's in the numerator and the derivative of what's in the denominator. So here we go. Now when you're doing these problems, I ask that you actually do the work. So you're saying I'm going to take the limit as x approaches 1 of the natural log of 1 over 1 minus 1. Well, that gives me 0 over 0, because the natural log of 1 is 0, 1 minus 1 is 0. If I get that, then I'm going to write here, I'm going to use L'Hopital's. This is what I'm expecting you to do on a test. So please, I want you to show me that it's 0, 0, infinity over infinity. I want you to show me what it evaluated to. I then want you to tell me LH, saying I'm applying L'Hopital's. Then I'll take the derivative. The derivative of ln of x is 1 over x, and the derivative of x minus 1 is just 1. So I get 1 over x. So we're looking at the limit as x approaches 1 of 1 over x. Well, that whole thing goes to 1. And that's what this, and that's how we're going to do this. Let's see another example. I'm looking at the cosine of x minus 1. So I'm going to look at the limit. The limit as x approaches 0. Cosine of 0 minus 1 over 0. Well, that's 1 minus 1 over 0, or 0 over 0. So I'm justifying I have a 0 over 0, which now allows me to say I can use L'Hopital's. Taking the derivative of cosine, I get minus sine of x. Derivative of 1 is 0. And derivative of x is 1. So this is really just the minus sign of x. So I want to take the limit as x approaches 0 of the opposite of sine of x. Well, sine of 0 is 0, so my answer is 0. Now we're going to look at this, e to the x. If I don't know what e to the x looks like, it's an exponential function. So as e goes to infinity, this whole thing goes to infinity. As x goes to infinity, and I square it, it's still going to infinity. So I have an infinity over infinity. And on your test, I would allow you to not have to show me the evaluation, but just show infinity and infinity. Now you would have to tell me what L'Hopital's. Derivative of e to the x is e to the x. Derivative 2 of x squared is 2x. So I'm going to look at the limit as x approaches infinity of e to the x over 2 to the x, 2 times x. Well, then again, I still get infinity over infinity. So see, sometimes we have to apply L'Hopital's a second time. So I'm going to apply L'Hopital's again. I get e to the x all over 2. I'm going to look at the limit as x approaches infinity. And I get infinity over 2, which is infinity. So we're saying that the answer is it goes to infinity. It doesn't, what we're going to learn later, it doesn't converge to anything. So here's another example. I'm going to look at x going to infinity. That turns out to be the natural log. Again, the natural log looks like this. So I get infinity. The denominator goes to infinity. It allows me to use L'Hopital's. I got a 1 over x. The cube root of x is the same thing as x to the 1/3. So I got a 1/3 x to the minus 2/3. And that cleans up to be x to the minus 1/3. So I end up with the limit as x approaches infinity of 3 over x to the 1/3. Well, that works out nicely because I have a 3 over infinity. That whole thing's going to go to 0. So these aren't really bad. This is actually not a bad section. It's a section where it becomes tedious because there's a lot of things and you need to check. You need to check because sometimes you think you have one thing and you don't. I'm going to look at this. I get a 0. Subtract 0 over 0. That's 0 over 0. That allows me to apply L'Hopital's. And when I do that, the derivative of tangent is secant squared x. Derivative of x is 1, 3x squared. So we're looking at the limit as x approaches 0. And I get 1 minus 1 over 0, or 0 over 0. Again, what does that say to do? 0 over 0. And it's another time to apply L'Hopital's. So I take the derivative of secant squared, bring down the 2, leave the secant alone, make 2 a 1, multiply that by the derivative now of secant. The derivative of secant is secant x tan x. And I write that all over. The derivative of 3x squared becomes 6x. Now I'm going to clean this all up. I'm looking at the limit as x approaches 0 of 2 secant squared x tan x all over 6x. Well, I can clean that up. I can cancel some things. So I'm really looking at the limit as x approaches 0 of secant squared x tan x over 3x, because I canceled out the 2 and the 6. Now, I can look at this and play around, and I'm still not going to get an answer I like because tan is going to go to 0. I got 0 over 0, but I could say, well, the limit of the the limit of the products, excuse me, the limit of the products is equal to the product of the limits. What does that mean? Well, I can look at the limit as x approaches 0 and evaluate the secant squared x over 3 and multiply that by the limit as x approaches 0 of the tan of x over x. Well, the numerator for here is a 1. So this whole thing is a 1/3. This on the right hand side is a 0 over 0. So I'm going to use L'Hopital's, but this time only on the right hand side. The derivative of tangent x is secant squared x. Derivative of x is 1, so I'm looking at the limit as x approaches 0 of secant squared x. Well, that's equal to 1. So that's the one that is the other limit. And I said they're products because it's the limit of this, of the limit as x approaches 0 of secant squared x over 3 times the limit as x approaches 0 of tangent x over x. And then we did the L'Hopital, so I have 1/3 times 1, or the limit is just 1/3. So here we are. We're going to look at this. Oh, I could see this must be 0 over 0. So I'm just going to apply L'Hopital's. Well, that's wrong. I'm assuming it's 0 over 0. I didn't actually evaluate this. Let's evaluate this. The limit as x approaches pi from the left, the sine of pi over 1 minus the cosine of pi. Well, that's 0. Sorry. This part here is a minus 1. So I have the limit as x approaches pi from the left of 0 over 1 minus a minus 1, or 0 over 2, which is 0. See, we can't just look at this and go, oh, it's L'Hopital's, because we're in the L'Hopital section, right? We actually have to evaluate it. There's a reason why we evaluate these things. We don't just assume. You don't say, oh, I'm in this section, that's what I need to do. Again, I'm not going to just arbitrarily start applying L'Hopital's and think it's 0, 0, because it is. I mean, if I evaluate this, I get 0 over 0, and I can apply L'Hopital's. Or I can be smart. I can't use major players because this isn't the limit as x approaches infinity. But I can look at it as the limit as x approaches 1. X to the 12th minus 1 can be factored to this, all over x to the 6th minus 1. They cancel. I'm looking at the limit as x approaches 1 of x to the 6th plus 1, which is 2. So I can evaluate this, and I don't have to apply L'Hopital's. Not everything is a L'Hopital's problem. All right, so I work this out. I get negative infinity over 0. So I don't like that. So I said, well, how about if I play around with it? Rewrite it as an equivalent. Well, 1 over x times the natural log of x. That's an equivalent. And when I do that, I get an infinity, because 1 over 0 is infinity, times a minus infinity. Well, they're both infinities getting multiply each other, and the answer is negative infinity. So really, this wasn't a L'Hopital's candidate. Here's another. I'm going to evaluate that. The arc sine of 0 is 0, and 0 in the denominator, so it's a L'Hopital's problem. So I apply L'Hopital's. You are supposed to know how to take the derivative of arcsine. That's 1 over 1 minus x squared, and take the square root of that. Derivative of x is 1, so I'm looking at 1 over 1 minus x squared square root. So I want the limit as x approaches 0 of 1 over 1 minus x squared square root. I put that in there, put 0 in for x, and I get 1, as you can see. So we've seen the majority of the L'Hopital's types of problems. We've done a lot. But here, there's other forms, right? If I have a 0 over 0 or infinity over infinity, it's a straightforward use L'Hopital's rules. But the problem is, what happens if I have 0 times infinity? It doesn't necessarily mean it's 0. I know we learned that 0 times anything is 0, but infinity is a different beast. Infinity minus infinity, I don't know what that's going to be. It could be 0, it could be some number. I don't know what these infinities are. 0 to the infinity power, well, is it really 0? We're approaching 0, so these are numbers getting closer and closer to 0, but they're not quite 0. So I can't say it's 0. And infinity to 0 power is not going to be 1. I know we say anything to the 0 power is 1, but it's not. Not when it's a summation of things. And if I get 1 to the infinity, it's not necessarily 1, because again, we're not exactly 1. We're getting closer and closer to 1 as x approaches whatever that value is. So here's an example to see why 0 times infinity isn't necessarily 0. If I evaluate this as x approaches infinity, this becomes an infinity, and that becomes a 0. Well, it's not. The limit of this thing is 2. Why? Because these x's would cancel each other out. I still have to do the algebra. And then you see the next two, they're the exact same examples. So here's an example of a 0 times infinity. It says, I want to rewrite the product of f times g as an f divided by 1 over g, or g divided by 1 over f, because they're equivalent, right? We don't divide with fractions, we multiply by the reciprocal. So f over 1 times g is really f times the reciprocal of 1 over g, or g. So algebraically, they're the exact same thing. We haven't changed the problem. So let's see an example. If I look at this and I say the limit as x approaches 0 from the left, from the right that is, sorry, I get a 0 times minus infinity. Well, that's a problem. So I'm going to look at the limit as x approaches 0, and I'm going to rewrite that as the natural log of x all over 1 over x. Well, if I do that, as it approaches infinity, I get an infinity over infinity. And I know I didn't write the minus. It's okay. The whole idea is I want to see where I'm going. I have some infinity over another infinity. This allows me, again, to apply L'Hopital's, and I continue to write LH, so you know what I'm doing. I'm continuing justifying by saying it's a negative infinity over infinity. The natural log of x is 1 over x when I take the derivative of that. 1 over x is the same thing as x to the minus 1. If I take the derivative of that, I have this, or negative 1 over x squared. It's a complex fraction. I should know how to work these out if I don't. Negative 1 over x multiplied by, whoops, not negative 1. 1 over x multiplied by the reciprocal of x squared over negative 1. These are algebra skills that we're supposed to know. So now I'm looking at the limit as x approaches 0 of minus x. Well, that's going to be 0. Here's another example. When I evaluate this, when sine of 0, that's 0. And then again, this is negative infinity. I don't like that, so I'm going to rewrite that. I'm going to rewrite this as the limit as x approaches 0 from the right of the natural log of x all over 1 over sine x. Well, I could say, well, I could clean that up a little. The limit as x approaches 0 from the right of the natural log of x cosecant x. And if I evaluate that at 0, I get infinity over infinity. That allows me to apply the L'Hopital's. As I show you, I'm keep justifying everything I'm doing. Natural log of x is 1 over x when I take the derivative. The derivative of cosecant is minus cosecant x cotangent x. So I can clean that up a little. And cosecant x is minus 1 over sine of x. And I'm multiplying that by cosine of x over sine of x. I know this seems a little silly the way I'm writing it out, but I'm doing it for myself to keep some things straight. I want to look at the limit as x approaches 0 from the right. Well, I could write this instead of a complex fraction. I could write it as a bunch of things being multiplied by each other. So that's being divided, so I multiply by its reciprocal, minus sine x. The reciprocal cosecant of cotangent is tangent. So now that's what I have. And if I try to evaluate this as x approaches 0, this part goes to 0. These two here, I get a 0 over 0, because I'm going to rewrite that part as sine x over x. That's why I have the 0 over 0. So again, I showed you a few slides before. The product of the limits is equal to the limit of the product. So I know on the right-hand side I have a 0. I don't know what happens over here yet, all right, because I'm following these steps. So I'm going to evaluate that. Since I do have a 0 over 0, I'm allowed to apply L'Hopital's. And the derivative of minus sine of x is cosine of x negative all over 1. And if I'm looking at the limit as x approaches 0 from the right of minus cosine of x over 1, I get 1 negative. So now I have a negative 1 multiplied by 0. All right, because the 0, the 0 came from up here again, and the 1 is the other. When I multiply them together, I get 0. So the limit of this thing is just 0. We're almost done this section. We have a few more slides left. Here's another form, combining into one expression. So I'm going to give you the limit as x approaches pi over 2 from the left of secant x subtract tan x. When I look at this, I end up with a 0. Oops, I'm on the wrong slide. Did I skip a slide? Yeah, sorry. When I do this, I end up with secant x gives me infinity, subtract infinity. So instead of leaving it like that, which I don't get an answer, I can rewrite them. That's the nice thing about trig functions. I can rewrite them in terms of sines and cosines. So I'm going to do that now. Limit as x approaches pi over 2 from the left. Instead of secant x, I could say 1 over cosine x. Instead of tangent x, I could say sine of x over cosine of x. Well, then I can combine them. I have the limit as x approaches pi over 2 from the left of 1 minus sine of x all over cosine of x. Now when I do this, I end up with a 0 over 0. I don't like that, so I'm going to apply L'Hopital's. And again, as I keep showing you, I justify the use of L'Hopital's. I'm saying I'm using L'Hopital's. I take the derivative of 1 is 0, derivative of minus sine of x is minus cosine of x. Derivative of cosine of x is a minus sine of x. So I'm looking at the limit as x approaches pi over 2 from the left of cosine of x, sine of x, and I get a 0 over 1, which is 0. And that's my answer. This does have a limit. Here's another to look at. As I look as x approaches infinity, this part here goes to 0. This bit here, the 3x, that goes to infinity. So I end up with a 1 raised to the infinity power. It's not necessarily 1. Remember, I'm getting closer and closer to 1, so I can't say this answer is 1. So how do I do this? This one has its own rules. I'm going to do this every single time. I'm going to say y is equal to 1 plus 2 over x, 3x. Then I'm going to apply the natural log to both sides. I'm going to kick out the exponent. Remember, you have the log of a to the r is equal to r log a. I still want the limit as x approaches infinity. And when I evaluate that, all I'm concerned about is not the left-hand side, but just the right-hand side. The left-hand side will take care of itself. I'm going to work on the right-hand side. I have an infinity, and that's a 0. I could rewrite this. And we've done that in the last section, so I'm just going to write the limit as x approaches infinity of 3 ln of 1 plus 2 over x all over the x. Oops, not over x, but 1 over x. I have to write an equivalent. When I evaluate that, I get a 0 over 0. Because the natural log of 1 plus 2 over x is really looking at the natural log of 1. Natural log of 1 is 0. 0 times 3 is 0. 1 over infinity goes to 0. So now, this one gets a little long. I'm going to apply L'Hopital's. I'm going to take the derivative of the numerator, 3. The derivative of this, which is I write it 1 over 1 plus 2 over x, times the derivative of that thing, which is a minus 2x to the minus 2, right? Because 1 plus 2 over x, when I take the derivative, this goes to 0. I already have 2 times x to the minus 1. Derivative of that is minus 2, x to the minus 2. That's where it comes from. Then I take the derivative of 1 over x. That gives me a minus x to the minus 2. Well, that's nice. Because if we're paying attention, we have some things we can cancel out real quick. So let's cancel out the negative. Let's cancel out the x minus 2's. So now I have the limit as x approaches infinity of 3 times 2, 6, all over 1 plus 2 over x. Now as x approaches 0, as x approaches infinity, this part here goes to 0. So I have 6 over 1, or 6. But we have to remember that we were saying the natural log of y is equal to 6. I want to know what y is equal, because that's where we started. Remember, we started all the way up here. Y equals. So I need to find out what y equals. Well, y is equal to, and I'm going to rewrite this as an exponential, e to the 6. Remember that the log ax equals y means a to the y is equal to x. These are things we're supposed to know. So our answer is e to the 6th. We're going to do the same thing here. I get a 0 to the 0. 0 raised to the 0 power. So I'm going to say, I'm going to rewrite this as, I'm going to shortcut this a little. The limit as x approaches 0 from the right of the natural log of y, because that's where we're going. Kicking out that exponent, the natural log of x. This gives me a 0 times a negative infinity. I will rewrite this, the limit, as x approaches 0 to the right, of the natural log of x all over 1 over x squared. When I evaluate that at 0, I get 0 over 0. I've justified the use of L'Hopital's. Take the derivative of natural log of x as 1 over x. And the derivative of 1 over x squared is minus 2 over x cubed. That simplified becomes 1 over negative 2 x squared. That's nice because I'm looking at the limit as x approaches 0 from the right of 1 negative 1/2 x squared. Well, that's all going to go to 0. But we have to remember, natural log of y is equal to 0. E to the 0 is what y equals, and that's just 1. So this thing approaches 1. We're getting ready for the next one, and this is to be the last one we're going to cover today. I'm able to evaluate this using major players because x is going to infinity. At least for the inside, that's a 1. This x here goes to infinity. So I'm going to rewrite this. The limit as x approaches infinity. Remember, we write this as the natural log of y is equal to, kick the exponent out, the natural log of x over x plus 1. That's going to give me an infinity times 0 because of the major players, which is okay. I can rewrite this. The limit as x approaches infinity of the natural log of x over x plus 1 all over 1 over x. When I evaluate that, as it goes to infinity, I get a 0 over 0. Wonderful. I'm now allowed to apply L'Hopital's. And I'm going to take the reciprocal of what's inside the natural log of x, x plus 1 over x. I'm going to multiply by the derivative of x over x plus 1. Now, that is a quotient. I get x plus 1 quantity squared. Then I end up with derivative of x times the denominator, x plus 1. Subtract the derivative of the denominator times the numerator, minus x. And then this part here gives me minus x to the minus 2. I can clean this up. I'm looking again at the limit as x approaches infinity. I have an x plus 1 over x multiplied by 1 over x plus 1 quantity squared all over negative x to the minus 2. This looks nice because I can cancel some things out. This x plus 1 cancels out with one of these. And I can do some more cancellations. And I end up with a minus x squared all over x times x plus 1. And that's going to reduce to minus x over x plus 1. So what we're looking at is the limit as x approaches infinity of minus x over x plus 1. I can look at the major players, and I go to negative 1. But I need to remember one important thing. That's the natural log of y is equal to negative 1. Or e to the negative 1 is equal to y. Or I could write that as 1 over e. That is everything in this section. This is going to be the material for your second test. This will conclude what we have today. Hopefully, if you have any questions, you can ask about it. This isn't a really hard section, and hopefully you're getting this. Thank you very much for your time, and I look forward to seeing you in your next class.